Swayam Prabha. Digital India. Educated India.
So, last class I have discussed that how you will determine the subgrade modulus and what are the different corrections such as the size correction, shape correction and the depth correction. And now today I will discuss the for different correlations by which also you can determine the k value, and then other methods by which you can determine the k value. Now, the basic also given correlation by which you can determine the subgrade modulus, where Es is the elastic modulus of the soil and B is the width of the foundation, in Ei is the bending rigidity of the foundation. That means, E is the elastic modulus of the foundation material and I is the moment of inertia. Okay. And mu is the Poisson ratio of the soil. So, if you use this correlation, then also you will get the k value for a particular foundation or particular soil, where the foundation and soil interaction both are considered. Now, few comments that when you do the plate load test, that your plate size should be taken in such that at least 10 to 15% of the foundation area is covered by the plate size. Okay. Then plates should be located at a depth equal to the foundation. If not, then you have to apply the foundation depth corrections, and sometimes it is given that the depth correction is given for surface plate. That means, the plate load test is done on a surface. Okay, but sometimes it can be done, or it may be done a certain depth, but that is less than the depth of the foundation. So, in that case also you have to apply the depth correction, but in that case the depth of foundation should be the difference between the depth of plate and depth of foundation. Remember that. If it is surface, then the depth of foundation is equal to the depth of footing where you are placed your foundation. But if the plate load test is done at a certain depth, but less than the depth of foundation, then your depth of foundation in the equation given in the depth correction factor will be the difference between the depth of foundation and the depth of plate. Clear? Okay, so that means the modulus of subgrade reaction may be taken as a constant up to a bearing values or up about half the ultimate bearing capacity of the subgrade. So, that means the generally the stress strain curve is taken as or the k value is taken as constant up to a stress which is equal to the half of the bearing capacity of the subgrade soil. Now, this I have discussed the determination of modulus of subgrade reaction by using plate load test. I have given some correlations also, but the plate load test can also be determined by triaxial test, then severe test and oedometer test also, or consolidation test also. And we have the correlations between these severe value and the subgrade modulus value. So, you can do the severe test, and then you can use those correlations to get the subgrade modulus. But here for foundation engineering, we prefer to conduct the plate load test, and from that plate load test we try to determine the subgrade modulus. Now, these are the some ranges of different subgrade modulus for different soil. So, loose sand to clay. So, this is the range that also you can use for your analysis purpose if you do not have the actual subgrade modulus value for a particular soil. And QU is the QU is the 2 times of CUU. That means the QU is 2 times of the CU undrained cohesion. So, that means this is called this unconfined compressive strength of the soil, that is QU, if the which is equal to twice the undrained cohesion of the soil. Now, we are talking about the Winkler spring, Winkler model. So, Winkler model has few limitations. What are those limitations? That one limitation is there is no connectivity between the springs. That means, but in actual foundation, these springs are, I mean, these soil layers are connected. That means, soil not layers. That means, once you apply a deformation, apply a load on a foundation, it will deform, but the deformation will not be only the loaded region. The deformation will be beyond the loaded region also, and deformation will be within the foundation also. But as there is no connection between these springs, so deformation will be only the loaded region. It will not be the beyond the loaded region. But actually in foundation, the deformation will be the loaded region as well as the outside the loaded region. For example, if we have a foundation and if we place it on the soil, so the deformation will be something like this. Okay? Suppose this is your say ground surface. So, that means the deformation beyond the loaded region is observed, but as there is no connectivity between the Winkler spring. So, in such case, if this is your foundation or this is the loaded region, so your spring will deform only within the loaded region. Okay? So, you will not get any deformation outside the loaded region. So, outside the loaded region, there will be no deformation. So, this is one of the limitations of the Winkler model. Then this is the linear response, that means the Q is equal to K into W. That means as you increase the stress, your settlement will increase. So, it is linear, but actual case this stress strain or stress versus settlement response is not linear. It is linear up to certain stress level or strain level, but after that it will become non-linear, but that effect is not incorporated in the Winkler spring. So, as the mentioned, deflection is confined within the loaded region, and another limitation is we know that for flexible footing and the rigid footing, both the cases deformation pattern are not same, because for the rigid footing your deformation is more or less uniform type. Okay, and the flexible footing, as I have drawn that at the center the deformation will be more, and at the edge deformation will be less. But for Winkler spring, whether your foundation is a flexible or the rigid, for Winkler model your deformation will be uniform. Okay, but unless you do something else, for example, if you take the stiffer spring at the edge and weaker spring at the bottom at the middle, then you will get a stiffer spring, you will get the less deformation, because if you increase the K value, definitely W value will decrease. So, if you as the edge, if you put the stiffer spring and at the bottom at the middle you use the weaker spring, then definitely at the middle you will get the more deformation compared to the edge of the foundation. But that can be achieved, but in normal case, if you consider the uniform K value along the length of the foundation or width of the foundation, then whether it is a flexible foundation or the rigid foundation, your deformation will be constant or uniform. So, that is another limitation. So, now we have to remove all these limitations. So, to remove that connectivity issue, the Filonenko and Brodich proposed a model where these springs are connected by a stretch membrane. Suppose these are the springs. So, these are connected by a stretch membrane. So, this is equal to T. Okay. Now, if you apply the load, suppose these are the spring. Now, if you apply the load, then what will happen? Then not only that spring, then the outside spring will also be deformed. Okay? There will be deformation of the outside spring also, but not that equal amount at the middle spring, but there will be some influence to the outside spring or the other spring due to the application of the load, as now the springs are connected with this stretch membrane. Okay. So, now I can given the equation for in such case, suppose for a xy plane, if it is we are applying a stress on a xy plane, suppose this is y, this is x and this is the loaded region. Okay. And below that we are applying, we have idealized the soil with spring. In such case, this is equal to k into w. So, this was the equation for the Winkler model, but now for this particular model, this is equal to T into delta square W x y, where delta square is del square divided by del x square plus del square divided by del y square. So, finally, this equation will be q x y k w x y minus T, then del square w x y del x square plus del square w x y del y square. Okay. And now, for the strip loading or the continuous loading, strip loading means where the length of the loaded region is much longer than the width of the loaded region. In such case, you have only x direction you will get the influence, the vertical direction will not get any influence, or that is called that plane strain condition. So, that means in such case q x will be equal to k into w x minus T d square w dx square. Okay. Or simple I can write q into k w minus T d square w dx square, this will be x. Okay. Or finally, I can write, but this is I can write this equation, but this is for strip loading, but for this rectangular loading, this is the equation. Okay. So, now this connectivity issue is been solved by using this membrane, which is T. So, that means the individual springs are connected by a thick elastic membrane under the constant tension of T. So, this membrane is under tension of T. Now, the next model is proposed by the Pasternak, where the springs are connected with a shear layer, because in the initial model, the first model or the second model, that your Filorenko and Bodic model, the determination of this T is very confusing, that which value we will consider for T. Okay. So, to represent the real soil condition, this model is more suitable. Okay, or more it can be applicable for this real life problem also. For example, suppose we have a soft clay layer. Okay. So, we have a soft clay layer and it is obvious that if the soil is very soft, then you have to put some sand layer over the soft clay layer, so that we can construct or do the construction, or we can increase the bearing capacity of the soil by putting that sand layer. Or sometimes the sand layer and the soft clay layer, or the placing of sand layer over the soft clay layer is very common to increase the load carrying capacity. So, now if we do that kind of situation, that means this is a sand layer, and then we place the foundation over there. So, this situation can be represented by the Winkler model. So, what is that model? So, Winkler model, these springs are connected with a shear layer. Okay, so these are springs with K is the spring constant or subgrade modulus. So, which is this is a shear layer. So, whose shear modulus is G. So, this is the subgrade modulus, G is the shear modulus, and this is the H is the thickness of the shear layer. So, in this way the connectivity issue is been solved, because this all the springs is now connected with the shear layer. Now, once you do the apply the stress over this springs or over this layer, so there will be a deformation like this. Okay. So, you can see that not only the loaded region, the region beyond the loaded zone is also deformed because of this connection between the spring with the shear layer. Okay. And this is representing this condition. Okay. That means the sand layer which is represented by the shear layer, and the soft layer which is idealized by the springs. Okay. So, that means we can now determine the shear layer also for this sandy soil. If I know the shear layer for this sand, that we can use as a shear layer for this G value as shear modulus for the shear layer, and the properties of the subgrade modulus for the soft clay can be used for as the properties of this spring constant or the subgrade modulus. Now, here the equation will be for a xy plane is equal to Kw xy minus GH square WXY. Okay, so, finally, I can write that QXY is equal to KW XY minus GH, then del square WXY, then del square x del x square plus del square WXY by del y square. Okay, again for strip loading, the equation will be simple W x into K W Q x into K W x minus G H d square W dx square, or simple Q equal to K minus G H d square W dx square. So, this is the equation under strip loading. So, in the Winkler model, the only parameter was involved is K, that means the shear modulus, but for the Filodenko and Bordich model, two parameters were involved, one is T, another is the K. But here also Pasternak model also two parameters are involved, one is K, that is the subgrade modulus, another is the G, the shear modulus of the shear layer. H is the thickness, it is not a parameter of the soil parameter. So, that is why these models are called 2-parameter model, and the Winkler model is 1-parameter model. So that means this connectivity things are solved. Then this nonlinearity is also incorporated in these equations, because in this particular course or these classes I will consider only the linear part. But nonlinearity can be incorporated. Then the time dependent, because here as I mentioned here, there's this only the k value is given and g value is given, but there is no time dependent phenomena is incorporated here. But that can be done, and it is already been done by the researchers to incorporate the time dependent effect into this model by replacing this spring with spring and dashpot. That means the spring will give you that settlement and the dashpot will give you the time dependent behavior. So that means if you replace the spring with spring and dashpot, then you can incorporate the time dependent behavior into these models also. That means the connectivity issues is solved. Then your deformation is not only confined into the loaded region, you will get the deformation outside the loaded region. Then you can incorporate the nonlinearity effect, because and then you can incorporate the time dependent effect. So all these effects are now being incorporated in these models. Okay. Now, in the next model that I will discuss about the Hettini model. So, where the individual springs are connected by a elastic plate or elastic beam. Okay. So, now here our beams on elastic foundation concept will start. That means here these springs are all connected with elastic your beam. For example, that if this is the spring, now these springs are connected with a beam. Okay. So, this is P is the force which is acting. So, this is the beam, this can be plate also beam. So, now in previous model that the interaction between the foundation and soil was not considered, it is only the soil, but now in this case if the foundation is idealized with beam or plate, and then the soil is idealized with these mechanical elements, that means either spring or spring dashpot, and now there is an interaction between this plate element or the beam element with this mechanical elements. Okay, now here also this connectivity issues can be solved, and now the loaded region will not be confined within the settlement will not be confined within the loaded region. Now again that nonlinearity, time dependent effect, all this can be incorporated. Now the question is, as I mentioned, that settlement cannot be confined within the loaded region, but if this beam is resting on a spring only, then again this settlement will be confined within the loaded region. But if you want to get the settlement beyond the loaded region, which is the actual case, then you have to place this beam on 2-parameter model. So that means this is the beam on Winkler model or Winkler spring. Now if you place the beam on 2-parameter model, so this is the 2-parameter model, this is your shear layer, this is your spring, now you place the beam over here. So this is basically beam, a load is applied, this is shear layer whose shear modulus is G, this is the thickness of the shear layer, and this is the K, and beam has a EI, this is the flexural rigidity. Okay. So now if we place the beam on 2-parameter model, then you will get the deformation beyond the loaded region also. Okay. So I will discuss these both cases, beam resting on only spring and beam resting on two parameter model. So, this is on spring, then beam on, this is beam on two parameter model. Okay. So, I will discuss these both the cases, and now this beam can be infinite, it can be semi infinite, it can be finite also. Okay. So, when the application area, infinite beam can be applied by railroad tracks, long strip footing and combined footing. For example, the rail track can be idealized by an infinite beam. Suppose you have a long strip footing, that means this is the say footing where this is the B, I am drawing the plan, and this is the L. Okay, and your L is much larger than B. Then you can idealize this footing as a infinite plate. Suppose you have a combined footing, suppose you have a column and those columns are provide a single foundation. Again, this is equal to B and this is equal to L. Then again L is much larger than B. Then also you can idealize this foundation as a infinite beam. So, in such case there will be multiple number of concentrated load which is coming from the column. So, that means in such case your foundation will be, that means here this is the beam and there will be n number of concentrated load. Okay, so that can be idealized as an infinite beam. Okay, then there will be semi infinite beam where one side is fixed or hinged or free, then another side is infinite. And then is a finite length beam also, that is for the your strip footing, your combined footing. So, where it is a finite length, that means any foundation whose length is finite. Okay, so this is the length of the beam which is finite, and if I draw the say your cross section of this beam, so I will get this type of cross section. But one thing I want to mention that, sir, if the beam is infinite, suppose if the beam is infinite, so definitely it has a finite width. So, infinite beam, then your width is finite. Okay? But if you have a finite width length beam, then there is a possibility that your length of the beam can be the distance I mean this is the length of the beam, and the length of the beam or the dimension of the beam perpendicular to this direction can be infinite. In such case, what we will do, we will consider the width of the beam as a unit. For example, if your length of the beam is finite, then there is a possibility that beam will be in plane strain condition. Then beam may be in plane strain condition. Plane strain condition means the dimension of this beam along the perpendicular direction is is very much longer than the length of the beam. Okay? So, in such case this will be treated as finite beam in plane strain condition, where your width of the beam will be taken as 1 or unit. So, remember that suppose if this is the infinite beam, then you have a finite width of the beam. So, that and if it is a finite length of the beam, then there is a possibility that you have a beam will be under plane strain condition, and we have to consider B as a unit. So, that means beam can be under plane strain condition also. In such case, the beam width you have to consider unit. If beam has a finite width like this, then there is no issue. If beam has a finite width, then you will get the if I get the cross section. So, cross section is simple like this. This will be the equal to B and this is equal to H. Okay. But if this is like this, so that means here your beam is like this. Okay. And if you cut this section, there will be a strip. So, in that case, so this is beam under plane strain condition. So, in that case your B you have to consider unit. So, that means this will be your section where your this direction B will be 1 and H will be the thickness of the beam. So, here also H is the thickness of the beam. So, that means you remember that beam can have a finite width and infinite length, or it can have finite length and a unit width. That means it is under plane strain condition, where finite length of the beam is finite, but the dimension along the perpendicular distance is very large, where it is under plane strain condition and we have to consider B is equal to 1. So, that means beam can be under plane strain condition also. Then what is the application area? So, in the infinite beam with finite width, this is the rail track can be modeled like this. But if you have a long strip footing like this case, long strip footing, this is long strip footing. Okay, this is long strip footing. This can be modeled in two ways. One is, suppose it can consider as a this length of this footing is considered the length of the beam. That in that case it is an infinite beam, and width will be the width of the foundation. This is one way. Another way that it is modeled that this width of the beam is equal to length of the beam, and in such case the beam will be under plane strain condition, and in such case you have to consider a unit width equal to 1. So, that means this type of situation I can model in two ways. One is infinite beam and finite width, another the beam under plane strain condition. Okay? Because you can model in this type of problem in two ways. So, in such case, in first case, if it is infinite beam, the length is equal to the length of the foundation and width will be width of the foundation, simple. In second case, your width of the foundation will be the length of the beam, but as it is under plane strain condition, because in that case your distance perpendicular to the length is much longer. So, it is in plane strain condition. So, we have to consider as a unit width, B will be equal to 1. Okay? So, that means here length B will be equal to length of the footing and B will be equal to 1. And in this first case, your L will be equal to L and B will be equal to B, that means the width of the foundation. Okay? So, now here I should write that this is the length of the beam is equal to B and width of the beam is equal to 1, and here width of the beam will be equal to B, width of the foundation, and length of the beam will be equal to length of the foundation. Okay. So, this way under different condition we can use infinite beam, we can use semi infinite beam, or we can use beam with finite length also. And we can now beam can be on 2 parameter model, or beam can be on non-linear spin also. As I mentioned, I will concentrate only the beam on linear spin in this particular course. So, in the next class I will start the derivation. I will give you that if first case, as I have discussed, I will discuss the 2 cases. One is beam on spring, another beam is on 2 parameter model. So, in the next class I will discuss the beam resting on wingless spring. Then I will discuss about the beam resting on 2 parameter model. Thank you.